was. Okay. Yeah. Welcome everybody. It is a great pleasure to introduce Gero Friesecke. He's going to talk about crystallization.
So, thank you very much for the invitation to this wonderful school. Nice to be in London, and special thanks to Kubina and Mircea who wrote all the emails. So,
got all the money. They got all the money.
Oh, they got all the money.
Yes.
Here we go. So, yeah, so I want to talk about crystallization in classical particle systems, and classical particle systems are supposed to model nature. So I want to start with a slide about nature. So it so happens that at low temperature, very often atoms and molecules self-assemble in crystalline order and special shapes. So this phenomenon is called crystallization. So it's a prime example of self-organization. Yeah, so there's no external agent that puts the atoms and molecules in place. It's self-organized. So here's when you have a sort of 5-pence coin in your pocket, and you look at it under transmission electron micrograph. So it consists of copper, and so that's the atomic structure. So at this scale here, 5 nanometers, you see the individual atoms, and so there are regions where the copper is crystallized. In fact, it's not globally rigid, so here's another region where it's crystallized in a little bit of a different way, but that's life. So here's another one, that's a carbon nanotube. So that's a particularly famous structure because of its wonderful stiffness properties and not that old. So, and it's actually quite recent that you can image it. So what you see here is the electron density on the carbon nanotube. So that's done with a scanning tunneling microscope, so with an STM. And then here it's something we all would like to have, gold. So so here's some gold nanoclusters. So again, so in fact, so this kind of imaging of the nanoclusters is quite old, but even with the STM, it's difficult to see the individual atoms. So that's quite a recent reference by Azubel in Science. So where people finally managed to image the individual atoms in the nanocluster. And then, so it's not just atoms that self-assemble into crystalline order, but it's also biological structures, so viruses. So in fact, most viruses are either, so by the way, can you see this pointer, or can you see the other, can you see this pointer I'm moving now?
You can play with your 2 hands, 2 pointers.
I can, okay, you can see them both, very good. I think I played with mine. So want this out of the way. So that's a herpes B1. So that's a virus built from proteins. In fact, it has 2 different proteins. So many codes of viruses are built from proteins, and typically there's a very small number of proteins that compose them. And this has a kind of icosahedral structure. So if you look carefully, so the other ones, because so this is some kind of triangle here, yeah. So you see this is a kind of triangle here, and there's another triangle here, and so there's a corner protein. If you look carefully, it has a 5-fold symmetry because it has 5 neighbors, and this is a typical protein. It has 6 neighbors. Okay, so that's a herpes B1, and that's another famous example. So the tobacco mosaic virus. So this guy is built, the code of TMV is built by a single protein, which has about 5,000 atoms. And so I will talk more about this. Actually, this visualization is by myself because I did not like the way it was visualized. Whereas here the visualization is by Rochard. So it's a wonderful way of seeing these objects. Okay, so and a goal then of my talk is to work a bit towards understanding why this happens in mathematical models. But I will start by connecting the mathematical models to nature. Yeah, so I could have so my motivation is different from sphere packing or numerics. Okay, so I want to understand why crystallization happens in nature. So I have to start with mathematical models of nature. And so, so just to recap, so the crystallization problem in the physical sciences asks why do atoms and molecules assemble in crystalline order? Yeah, the sphere packing you see in the other part of the school. I have a little drawing here. It's actually by Kepler personally from 1611. So that's Kepler's drawing of the sphere packing. It's a neat drawing. And here's another example. So of course you have many objects that form crystal lattices. So here's a picture of the vortex lattice in Bose-Einstein condensates. So these are vortices in a quantum wave function. So, and of course, mathematically, all these problems are somehow related. So now let me go to the mathematical models. So there are basically three classes of models: molecular dynamics, statistical mechanics, and energy minimization. And so you have, let's say you have n particles. They have in RD, they have positions xi, momenta pi. So if you believe in molecular dynamics, you would solve an equation called the Langevin equation. So it's the following stochastic ODE, xi dot equals pi dot equals something, and it doesn't matter for the moment what it is, we go more into this. And there's a gradient of some energy appearing, and then there is a damping, and there is a noise, and there is a relation called fluctuation dissipation relation. So I will you don't need to take notes of this, so I will write down these models in more detail. So then there is statistical mechanics, where you say in equilibrium statistical mechanics, you don't have dynamics, you just model an ensemble of particles by a probability measure called the Gibbs measure, which is e to the minus beta times the Hamiltonian, which is something like this. And then there is energy minimization, where instead of looking at a probability distribution e to the minus beta h, you just try to find the argmin of the potential energy E. And so then finally there is a prototypical potential energy, which would be pairwise interactions with the Lennard-Jones potential. So so now the prototypical one would be this one here. So it looks like this. Okay, and my key point is, so these three models are connected by asymptotics. So there are two important asymptotic limits. So at long time, molecular dynamics goes to statistical mechanics, and at low temperature, statistical mechanics goes to energy minimization. So that's the connection between more fundamental models and energy minimization. And so so now, if we do mathematical theorems, we usually let a scale, we take a scaling limit. Yeah, we take an asymptotic limit in pretty much all of mathematics. They're used to taking asymptotic limits. So yesterday in Danilo's talk, we saw some type of thermodynamic limit where we went to infinite configurations and looked at the density, i.e. number of particles per unit volume, and fixed that, etc., etc. And so here's the long time and low temperature. And but in practice, nature doesn't wait till time has gone to infinity, and nature also doesn't set temperature equal to 0. But so time is finite and temperature is finite. Nevertheless, we expect that at long time and low temperature, crystallization should kind of happen. And so here is the simulation of this Langevin equation. So I randomly initialize my particles. So they evolve by Langevin dynamics now, and I let this run. Okay, so I put reflecting boundary conditions on the boundary of the box. So what do you think will happen? So 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 what happened here is I took an inverse temperature, which looks large in these units here, namely 4,000, but it's not large enough. So now I do something else. I make the temperature larger from 4,000, inverse temperature larger from 4,000 to 100,000. Okay, so that's a good inverse temperature now, 1/100,000, and I run my simulation again, same initial data. So what happens here is following. So you see that very slowly so maybe run it again. So slowly, but no, that was the wrong one. I'm the slow one. So okay, so let's do the low temperature one. So slowly, and so the particles form sort of little triangle configurations, and so to speak, I mean, for example, here, this configuration, it doesn't look perfect because you think you would get lower energy if you move this guy, which only has 2 neighbors. So what I would do if I was nature, I would move this guy kind of here. Okay, because here it has 2 neighbors, but if I put it here, in the bottom, it should have 3 neighbors. And very interestingly, nature finds a move of doing this. So that was the move that did it. Okay, so now it has okay, so here we go. So that's how this crystallization happens in nature. So this little cluster formed out of nowhere just by me running the thermodynamics and waiting long enough and taking the temperature low enough. So that's why asymptotic limits approximate nature. So now I also want to show you a different interaction, because this was very simple interaction where we assume identical particles that would work for noble gas atoms. Maybe we have sodium and chloride, so we have a slightly positively charged type of atom and a slightly negative charged type of atom. So I've put these atoms here, so I've colored them blue and red. So I still take the Lennard-Jones interaction here, but I take a plus-minus Coulomb repulsion in the energy. So plus-minus Coulomb repulsion means the usual thing. So blue and blue is plus Coulomb, blue and red is minus Coulomb, and red is plus Coulomb. Okay, so that's that. So what do you think happens here? So yeah, maybe there's somebody in the back. No, okay, yeah, okay. So I mean, you're a bit too sure of yourself, but you're trying to make an interesting point. So there are many analoga of Coulomb. Yeah. So if you say you want the Green's function of the Laplacian, or you want the unique rotationally symmetric divergence-free field outside zero, then it would be a log. In physical systems, if you have a 2-dimensional physical system, i.e., you have particles confined to a thin slice or a thin surface, charges still interact via the freezing coil. Okay? So that's the different story. So if you confine real atoms or ions like sodium and chloride into a thin 2-dimensional slab, they still interact via 1/r, not a log. So I mean, it's, and of course in some other context, it's the right thing to pass to the fundamental solution of the Laplacian, which is the log. But here it should really be the Coulomb. Okay, so but you know, thanks for the question. So my answer would be there are several good versions of Coulomb depending on what you know. Okay, so let's run this thing here and see what happens. So I also took the temperature very low here. I slowed it down to make you see what happens. So again, you see some kind of crystallization, but in fact you see a different lattice. Okay, So in 2 dimensions, if you have an interaction of this form, so which has 2 types of particles where like ones attract and unlike ones repel, so we see a piece of the square lattice. So it's not the triangular lattice, it's the square lattice. Okay, so one thing that we learned from this example, I put it on my slides, is to make the point that in nature, you very often see crystal structures, but the crystal structures you see depends on the type of atoms. So when you have something like equal noble gas atoms in 2 dimensions, it would be triangular, in 3 dimensions, it would be FCC or HCP. And in for sodium chloride, in fact, also in 3 dimensions, it forms a cubic lattice. Okay. So here we go. So now my course has several ingredients. I want to spend some time explaining these 2 scaling limits I took to connect a typical molecular dynamics simulation to energy minimization. So that will cost me about 45 minutes. And then once I am in energy minimization, I will spend most of my course talking about the following theorem here. So, okay, so even in 2 dimensions, for the standard Lennard-Jones, it's not known what the ground state is exactly. So there's some things are known about it, but it's not known what it is exactly. And I'm interested not in asymptotic crystallization theorems in the sense that, the crystalline configurations asymptotically to leading order achieve the best energy, but in exact crystallization theorems. And so when you make the interaction very short range, and in fact, so Heitmann and Radin in 1980 introduced the following beautiful model, which you should consider as an advanced version of sphere packing, and because the version is advanced, and the question they asked, rigorous results are limited to 2 dimensions. So if you pass to the limit, P goes to infinity in this Lennard-Jones, so you get the following energy. So it's kind of plus infinity for distance less than 1. So that's the forbidden configurations of Danilo. Then you get a reward of -1 at 0, and then you get 0 at r bigger than 1. So, so the particles would sort of like to stick to each other. They get a reward for sticking to each other. So they call it sticky disks, they call it. Okay, so and then the amazing fact is that for any number of particles, if you minimize this energy, so so some I less than j this, there's a global rigidity emerging, no defects, no nothing. So whatever you do, the ground states are subsets of the triangular lattice. And so I mean there also so here's a bit of literature. So there's a nice paper by Florian Theil from 2005, so where he showed something, I mean, sort of analogon to sphere packing in 2D. So it's a sort of asymptotic result, so that the minimum energy is the same as the minimum of the energy on lattice subsets plus little o of n for n particles, so for n large. So that's sort of on average, you cannot do better than the lattice. And in fact, this kind of ionic interaction I showed you, or something of this sort, with a very narrow, okay, so the Theil result is around in this regime here, so it's a very narrow and steep potential well. And then similarly to this, you can also add ionic interactions the way I've shown, and then you get this square lattice. Okay, so and for in 3D, as in sphere packing, nothing that's not computer aided. So here we go. So what we did is some years ago, but I think it's conceptually very interesting, is we wanted to reprove this result. So we didn't kind of like the way this was done, because it was clever estimates based on explicit values of the energy, but you don't see any structure, so things shouldn't depend on numerical values of minimum energies and stuff. So and there were like constants like 5 or 13 or 1 over this, and you don't know what they mean. So here's sort of the mission statement of my course, is that our lack of understanding of crystallization problems comes from the featureless energy formula in which all particles enter equally. So that is equally true of sphere packing and of energy minimization. And so people in my world, in the particle interaction world, like Heitmann, Radin, Tile, Maini, or Mr. Stefanelli at Vienna, so they established nice two-dimensional results via clever but highly technical bounds on these energies. And at the end of the day, it's like going to a restaurant and then you come out and you're still hungry. They leave you somehow with an empty stomach, because if you then ask yourself,
Nouvelle cuisine.
Hmm?
It's called Nouvelle cuisine.
Nouvelle cuisine, very good. Yeah, so Nouvelle cuisine is Heitmann, Radin, Tile, Maini, and Stefanelli. So I'm old style. I'm after understanding. Okay, so I like a good hearty meal. And now somehow there are things occurring in this configuration, especially surfaces, so boundaries and also defects. And so our idea was that one should account for this by some decomposition of the energy that goes away from this featureless formula where you have a sum over pairwise interactions, you see nothing, but decompose the energy and very, very, very carefully interpret the different terms. And then you can simplify proofs and go for open problems. So I think that this approach, okay, so we did a pitifully simple model with this approach, but it works. And I think it's a powerful approach. So here's some intuition for the Lennard-Jones. So this is the 612 Lennard-Jones. So I did so here's a configuration which is actually not a global minimizer, but close to it. So most things are crystallized. If you look at this very carefully, so maybe okay, so one way is to rotate your head like maybe try to rotate your head by almost 60 degrees, and then I show it here only for the online people, for the offline people. So do you see? So here's some kind of line of atoms coming in here, and you see this, and you tilt your head like this. So here's the line. So it's a very, very subtle configuration. It's a dislocation, and it's a numerical minimizer. And if you plot the energy per particle, so you get the following plot. Okay, so energy is mostly very small, and it's high here. So that's this core of the dislocation. Actually, that's the dislocation core, and it's high on the surfaces. In fact, where there's different orientations of the surface and different atoms have high energy. So the energy per atom is just for each interaction energy in the pairwise interaction, I assign half of it to one guy and the other half to the other guy. Okay, and then I plot the energy per particle. To me, this kind of plot gives an enormous intuition about what should happen, and so okay, and so the way we decompose the energy is by bringing in a new field of mathematics called discrete differential geometry. So that's a very nice field that emerged more recently, so in differential geometry, the key notion is curvature. Yeah, there are 1 million different curvatures. There's like scalar curvature, there's Ricci curvature, there's Riemann curvature, whatever, and the same happens in the discrete world. And so it turns out that it's very useful to endow these particle configurations not just with something like a metric or a graph structure where you draw the bond graph, but really introduce curvature on this. And then view the kind of defects as sources of curvature, and then what you gain from this, you have certain theorems in discrete differential geometry which you can then use. So in particular, stuff like when you integrate curvature over some large region, usually you get topological invariance. And so we started on this. Okay, I had some vague idea that when you want to do a local to global result in mathematics, so the best field for local to global results happens to be differential geometry. Yeah, so for example, there are theorems that when curvature is locally zero, then it's globally zero, or things like this. Or you can sometimes classify manifolds just by bounds on the curvature. So for example, you can characterize the sphere just by loose bounds on the curvature. Okay, and so here we also did something new with this method, so we could determine the uniqueness in the Heitman-Radian model. So here's our result, just to show a result at the beginning. So it's the minimizers of this Heitman-Radian energy. So once you see it, you might stop believing it's so extremely simple, because it's not. So for example, for 6 particles, there are 3 different minimizers. Yeah, so I don't know which one you find more intuitive, but they all have the same energy. Or for 9, I mean, this thing looks a bit weird because it's not even convex, but it's just as good as like this one. And we also worked out the sequence, so you get a unique minimizer if and only if the particle number belongs to a certain sequence. So when we found the sequence, the first thing we did was Google it. So on oeis.org, so it's the online encyclopedia of integer sequences. So so we typed in like the first 8 terms or so, and it already found it and gave us lots of references, and occurs in lots of problems. Okay, so it has some recursion relation, blah blah blah. So that's a nice resource if you do any kind of, if you have any funny sequence cropping up, it got really good. This I think up to 16. We go to 16 or 19. Okay, so yeah, of course. Here we go. So, and then maybe I do want to do an overview slide. It's a little bit complicated, but I think so. So to start with an overview slide on my course, and then we do details kind of things. So so the intuition would come really from physics or from continuum mechanics or coarse graining. So if you start with a general configuration, it would usually be not too bad, but it certainly might have defects, and it certainly might have, it must have surfaces, because real life doesn't happen on the torus where you can talk away the boundary, but real life happens in R3 or RD, and configurations have boundaries. So for large particle numbers, you expect some so the energy to have some expansion which has a lot of features. So instead of this, which is featureless, sum of pairwise interactions, some featureless thing. When you coarse grain, the heuristics tells you that you should have some kind of bulk type energy, which is an energy per particle, which happens when I deform the thing. So that's kind of bulk contribution, like an elastic energy. Then I would expect a sort of surface energy, which is of lower order, but that would go with the length and possibly the orientation of the surfaces. Then I should certainly have some penalty for the defects where it's not so clear how it scales. It's neither bulk nor surface. It will depend on the density of defects when you take the limit. So it could, so usually in interesting regimes, some log scale. Sorry? Oh, okay. So yeah, we come to that when we do discrete curvature. So there is a nice way of rigorously defining then this notion of discrete curvature. But let's say, so a rough definition would be you have locally the so it's an atom is a defect if it has locally a different number of nearest neighbors than a crystal reference lattice. So like 5 or 7 instead of 6 in the 2-dimension. So, but we certainly make rigorous properties. Okay, and then so then you get with luck some asymptotic decomposition into different contributions. But we thought we want something which is like asymptotics to all orders. So we have contributions. So we have an exact splitting into sort of defects, topological terms, surface term, bulk term, etc. And yeah, so defect penalty, elastic, crystalline. And so with this discrete differential geometry methods, at least in this simple limit here, there is a sort of exact decomposition like this. And when you do this, so with the exact decomposition, then okay, no, then yeah, no, maybe I wanna finish with this. So then once we have these individual terms, the strategy is to minimize them out individually. So you have a sort of perimeter term which wants a certain shape. You have a defect measure which presumably wants low defects. You have a topological term which is presumably independent of whatever else you do and can be taken out of the energy, which simplifies hugely, etc. So that's roughly the strategy. Go to such a decomposition and use curvature. Okay, so yeah, I think I want to go out of the screen share here, but go sort of back to this basic thesis, so that one should really decompose the energy into something that has more features. Okay, so let me stop my sharing here and maybe should I leave the Zoom? I think I should, right? I can, or at least I could. Zoom and then so then I'm going to talk a bit more about this.
So now we want to use the camera.
Yeah.
Okay.
Okay, yes. Oh, so can one see what I write here? So,
This one?
What?
No, this one they're using. No, but for the people online, they will see this one. You see, that's the problem.
Okay.
It's complicated.
Complicated but fancy equipment, definitely.
Yeah.
Very fancy.
So the people online follow this camera.
Okay. Well, that's fair enough if they follow this camera. I mean, they want to see what I write, right? They don't want to see what I say.
But is there not a way that it doesn't cover, like?
But I'm going to go outside and see.
Okay. So but you tell me when I should start. No image from the speaker, but just from the writing.
Okay. It's true that people are just seeing this one.
Very fancy equipment.
So
Yeah.
right in the middle of
That's how we did our hybrid.
Hmm?
That's how we did our hybrid lectures. With all of
Yeah,
this.
the hybrid.
Very, very stressful. It was really
Yeah.
stressful.
So
what is this computer from?
So,
maybe there's another camera.
so this, it's just to start to record now.
Ah, sure.
Anyway, nice to have a break. So that's
So this is the camera.
I think there are two cameras because this camera here shows nothing, right? And that's this one. This should also be.
So now, thank you.
Okay. So okay, so
I think it's going to be a problem here.
I think it goes the wrong way around because people need to.
No, it's a question of Spiegelverkehr. It's mirrored, then you have to.
Okay. Very good. So. Okay, but it's too slow when I write like this.
The people on Zoom are seeing it in the right direction.
But you guys are seeing it in the wrong direction. So
The people in Zoom are seeing
okay, I think Danilo found a fix yesterday. So
Okay.
okay, maybe yeah. Now the okay. So can you read this? Or is it too small? Can you read what I write? All right. Is that good? So yeah, particularly for those who are here. So the first part is I wanted to go from molecular dynamics to statistical mechanics and to energy minimization. So so that's a topic. I mean, of course. So I think Codina, for example, is an expert in statistical mechanics. She even did her PhD in statistical mechanics. Maybe not all of you know this, but yeah. So apologies to Codina. She will know everything I say, but on the other hand, I think my last lecture is especially for you, and I'm afraid nobody else will understand it. So now you suffer by being bored, but then maybe everybody else suffers when I talk about the Wigner crystal at the end of my lectures. Okay, so this is really basic modeling and sort of physics or whatever, or math. So you have particles. So they have positions xi and momenta pi. So you have n particles in Rd. But sort of one of the things about physical particles is that they don't just have positions, they also have velocities or momenta, i.e. mass times velocity is the momentum. So they're described by xi pi, I equals 1 to n. So these are the positions and the momenta. So real particles have positions and momenta, and dynamics depends on that. And so the Hamiltonian would be something like that, sum I equals 1 to n, and then you have the absolute value squared of the pi's divided by twice the masses plus v of x1, xn. And so the mi are the masses, and this is the interaction potential. And so then the standard equation you would have, so for start, what you learn usually at courses also in math departments is you go for the Hamiltonian dynamics. So this would be the following: xi dot equals pi, so 1 over mi pi, which is the same as the gradient with respect to the pi of the h, and the pi dot equals minus the gradient of the potential, so minus the gradient of the potential is the force. And then this is the same as minus the gradient with respect to xi of the h. So it has this nice symmetric form. So xi pi dot is a gradient and minus a gradient. Kind of flipped. So that's the Hamiltonian dynamics. And so the first question to answer is which potential. So then, so the true atoms, so then you have to find the potential quantum mechanically by introducing electronic structure and then minimizing out the electrons. That's called the Born-Oppenheimer approximation. And then you get an effective interaction energy, which just depends on the position of the atomic nuclei. So here we're gonna skip this step and not start at Adam and Eve or quantum mechanics, but already assume there is a potential energy surface. But what should we take? So which V should we take? And so I want to answer this with a quote from Richard Feynman. So he has a very nice quote about this. So no, so it's fine. It's fine. No. I mean, you know, you don't need to. You just give me a sign, and because I can see on the control scene much here. So Feynman says the following. So I want to write a Feynman quote on the board. So that's an immense pleasure because I've only shown it on slides, but never on the board. So I write it on the board. So it makes me feel like Feynman for 1 minute, you know. So he says. So Feynman was once asked if a Martian came to Earth and would ask you what's the most important thing about the Earth, then Feynman answered that he would answer the Martian the following quote. So that's what he said. So the most important thing about the Earth, according to Feynman, is all things are made of atoms, and these atoms so attracting each other when they are a little distance apart, but repelling each, repelling upon being squeezed into one another. In that one sentence, there is a lot of information about the world. Okay, so that's Feynman's quote. And so in terms of modeling, so the way I interpret the quote and everybody else is a good empirical model. If we have like atoms, we take the V is the sum I less than J of some potentials Vij of Xi minus Xj. And the V should look as follows. So it should look as follows. So that's the basic shape from the Feynman quote. So this is here Xi minus Xj, and this would be the Vij. So it doesn't really matter which types of atoms. You always have repulsion at short range and attraction at long range. And so if we have the prototype, so for example, for a gas of equal noble gas atoms. So for example, argon is a noble gas which is in the atmosphere. Actually, It's about 30% of the atmosphere is argon. It's very inert and it interacts like this. So then a good model is the Vij is the Lennard-Jones. So it's R to the minus 2p minus 2R to the minus p. So so this is the Lennard-Jones potential, and typically often people take p equal to 6, but it has not that much of a meaning. So when you take p equals 6, maybe the long range is correct for van der Waals forces, but the short range is not correct. It should be a Coulomb repulsion at short range, but empirically it's a good potential. And so so now I come to the, so now we figured out the V, so now I come to the problem, is that energy is conserved. So along solutions of H, so we basically have d dt H of x of t, p of t is identically equal to 0 along solutions of this thing. So yeah, so that's a problem because energy is conserved, but we as point configuration optimizers, we want to minimize energy. We don't want to conserve it, we want to minimize it. So let's ask this question maybe more scientifically. Can put it here? So yeah, actually I like your system, Kodina. I mean, it's a wonderful equipment at UCL. Maybe we should buy it for TU Munich. It's really great because you can sort of put the, you can rearrange the pages much nicer than on the laptop. So, okay, so here's a question. So should we conserve or minimize energy? So that's a seemingly elementary question, but it's not that elementary from a scientific point of view. So should we conserve or minimize energy? So any contributions from the audience? What should we do? Conserve or minimize?
First conserve, then minimize.
First conserve, then minimize. Okay, yeah, well, conserve. Well, okay. I mean, okay. So yeah. So let me answer this as follows. So that two kinds of systems, closed systems, so that do not interact with any environment, then usually the energy is conserved. So so if you have a closed system, so conserve, and in an open system, so let's say often it makes sense to minimize. Okay, so and in a closed system, so in mathematically this would be sort of Hamiltonian ODEs like this H I've shown, or if you're interested in hyperbolic PDEs. I'm very interested in partial differential equations, but yeah, hyperbolic PDEs would conserve energy. So, but here this would be more like so this would be let's say so stochastic ODEs are much better, and so and why stochastic? So you get a stochastic system that so stochastic ODEs model open systems, and they do model the environment by the stochasticity. So it's basically sort of if the environment is sufficiently, let's say, complex or random. So random is usually a proxy for very complex. Then you go into stochastic ODEs and also into parabolic PDEs. And I want to explain what happens here. So now let's go to molecular dynamics. So the right thing to do when you have an open system is that atoms can also lose energy, for example, by optical emission, by acoustic emission, by things like this, by emitting photons and so on. And so a basic model for this is called molecular dynamics. So that's the equation I showed you. So in Hamiltonian dynamics, I couldn't show you crystallization because it doesn't happen. So in molecular dynamics, it happens. So and that's the Langevin equation. So I modify my equation a little bit. So let's use this wonderful tool here. So to write the equation again, so we add a sort of stochastic term, and so we add stochastic forces. So we keep the first equation, and the second equation, pi dot equals minus grad xi v, and we add two terms. So there's a damping, like so. Yeah. So there's a damping and a noise. So W dot of t, so time derivative of Brownian motion. So this would be white noise, and this would be damping. And so let's call this molecular dynamics. So in fact, there are other variants of putting in the damping and the noise. So they go by the name of thermostats. And so, but that's the simplest one. And so gamma bigger than 0, sigma bigger than 0. And then there is a relation. So sigma squared is 2 gamma over beta. So let's call the fluctuation dissipation relation. So it's a fluctuation dissipation relation. And so beta here is the inverse temperature. So beta is the inverse temperature of the system. And so roughly speaking, this so very roughly, so this dynamics is dynamics is at constant temperature, not constant energy. So energy is not conserved because you kick it with a random force and you take out energy through the damping. But in this kind of dynamics, roughly speaking, the temperature is constant. And what that means, I want to explain. So it's really quite elementary, but usually you need to follow like a long course on statistical mechanics for like one semester, and I want to cut it short to like 10 minutes or whatever. Okay, so I want to cut it short to 10 minutes. So this equation is really quite interesting. So this Langevin equation. So to understand what's going on, we pass to densities. So if, let's say, xi0 and pi0, I equals 1 to n, if they're drawn randomly from some distribution rho naught of xp, so rho naught goes from R2d into R, so from some position and momentum distribution. So this is something like an ensemble of initial conditions. So then we get evolution equations for the densities. So for the Hamiltonian dynamics, so we get dt rho plus v dot grad rho equals to 0, where v is the Hamiltonian vector field, dh dp, dh dx, with the minus sign here, from R to the 2D into itself. Okay, so that's the equation. And because this vector field has this nice structure with a gradient with respect to P here and with respect to X here, so so this vector field has divergence 0, so I can rewrite it in even nicer form. So plus divergence of rho times V equals 0. So and this equation is called the Liouville equation. Okay, so that's for the Hamiltonian, and now let's see what happens for the so for the molecular dynamics. So for the Langevin equation, you get extra terms in the equation for the ensembles. So here we get something similar, plus divergence of rho V is equal to the divergence of gamma mass matrix inverse P rho plus a half sigma squared and a Laplacian, but only with respect to P of rho. And so this equation is called the kinetic Fokker-Planck equation. It's an important equation. Kinetic Fokker-Planck equation. So KFP, let's call it KFP. And if you want, so in stochastic terms, it's kind of the forward Kolmogorov equation for the stochastic differential equation. So so the forward Kolmogorov equation for the stochastic differential equation. And so let's do a toy proof of A. So proof of A, how to get the Liouville equation is super simple. So you basically do okay, so what happens here? So let's do a configuration space picture. Here's a phase space picture, sorry. So Z is XP. So you take some initial distribution, and then when you solve the ODE on the base space here, you get a point Z of T, but the density is just kind of transported under this flow. So if you take rho of ZT is the push forward of rho of Z0 under the flow of H. So sort of phi of Z naught T is the solution to H with so Z dot equals V of Z with initial condition Z of naught is Z naught. So that's sort of your flow map, and you just push forward. So that's basically the rho of phi inverse of ZT comma Z. Okay, so that's the push forward. So you evolve back and evaluate rho naught. So that gives you the probability. So and so you can just define the solution to be like this, make this ansatz, and then differentiate and just check it satisfies this. Okay, so so the proof of B. Okay, so I'm certainly not going to replace a course on stochastic analysis or stochastic processes. I cannot do that in 10 minutes, I'm afraid. So so that's but there is a recipe. So the general rule stochastic ODE to the PDE for the density, and the general rule is explained. So there's a Springer lecture notes by am I allowed to mention another London University at UCL, Codina? So he's at Imperial, okay? So Greg Pagliotis, so he's at Imperial, but these are nice lecture notes on stochastic processes, and he gives the rule. So whenever you have something like Z dot equals V of Z plus any matrix times Brownian motion, any matrix times Brownian motion, and then the density, so P of Z of T in A is like integral A rho of Z T dz. So that would be the definition of the density. So the thing that gives you the probability of being in a set A at time t. Then you get dt rho. So the PDE is dt rho plus divergence of rho v equals a half this matrix. So this is in our case in R to the 2D cross 2D. So it's a 2D by 2D matrix because the V is in R2D. So then you take this times its own transposed and then the scalar product with D squared rho. Okay, so if you apply this prescription, so you write the ODE, I mean you write it in a form, so the MD ODE, I think I have it here. Yeah, so somehow the noise sits only on one of the components, namely on the P. But if you write it in this Pavliotis, whatever standard vector valued form, and you use this rule, then you get the equation I've written. Okay, so if you either believe me or you check it at home. Okay, so that gives so
this matrix M is diagonal.
Okay, so the M, oh, the matrix M, I apologize sincerely. Yeah, so the matrix M, in my case, I had particles with masses. So so M is just diagonal with the masses. So it's M1 times identity D by D, M2 identity D by D dot dot dot. Okay.
Sorry, I just want to double check for the spaces in this instance. They're just you put the Euclidean spaces, right? There's no, we're talking about compact domains where we have to worry about boundaries.
No, I mean here we just evolve in RD, so I put no boundary conditions here. In the simulation I did because I didn't want to follow the particles all the way through RD, right. So I had to keep them in a box. But here I mean, of course they could be added, and producing extra terms.
No, I was just, I don't have a lot of experience with difference equations, so I just wanted to check those.
Yeah, no, absolutely. So okay, so and then maybe I should, I mean, really here, this is not 2D, I wrote something wrong here. So 2dn cross 2dn here. Okay, so because it's really the vector of the positions and momenta of all the particles. So the phase space has dimension 2D capital N. Okay, and then that's a matrix acting on this. Okay, but anyway, then you get this Fokker-Planck equation. Okay, so so here we go. So now so now this kinetic Fokker-Planck, so it has nice properties. It preserves probability. So total probability. So why is that? Well, if you look at this equation, I mean it is in divergence form, right? So this stuff here is also a divergence only with respect to P, but it's a divergence on the whole space of the yeah. So basically, if you integrate integral dt rho is basically 0 for solutions that are smooth and decay sufficiently fast. So preserves total probability, just like the heat equation. So the second thing is it also preserves positivity. So that's a little more interesting. So for example, when you just take the Liouville part, it preserves positivity because it's just transports densities. And then, so to speak, the parabolic part preserves positivity because of the maximum principle for the heat equation. Okay, and if you combine these two, it still preserves probability. You can, so for stochastics people, they would not worry about this because they say it's obvious from the definition because I defined the rho to be a probability before I derived the PDE. But you could also take a partial differential equations viewpoint, write down this equation, start with an initial condition which is positive, and then wonder whether there's a simple argument against this positive. Okay, and then we get back to the thing that it works at constant temperature, not constant energy. And so let's make this rigorous. So now that things are slowly becoming interesting. So there's the only theorem. So for nice vector fields V and nice initial conditions rho naught. So, you know, smooth, rapidly decaying, blah, blah, blah. So the free energy, so now the object to consider is the free energy F of rho. So it's not just integral R over 2nd H of xp rho of xpt dx dp. So you integrate the energy over phase space. So that's the many-body phase space here. The factor 2 for the momenta, the d for the dimension of the in which the particles move, and the n for the particle number. But now an extra term, beta inverse, so temperature times integral r to the 2nd, and then you have a rho log rho term, so just the Boltzmann entropy. So this thing is Lyapunov functional. Sorry. So it's for the KFP. So that's a kind of Lyapunov functional for the kinetic Fokker-Planck. So so here this rho log rho is basically looks more or less like this. It's a steep slope here, rho, and this is rho log rho. So that's the Boltzmann entropy here, and so this thing has this kinetic Fokker-Planck equation, which came from the prescription of writing down the evolution of the density for any stochastic ODE. So that has this very nice Lyapunov function. And so that's, if you want, the theorem that is the foundation of statistical mechanics. And so so I prepared some, so for maybe later this afternoon or tomorrow, we have to see how we schedule things. I want you to prove this in class. So in fact, it's not that simple. So if you just very naively differentiate, you get some horrible terms. So I structured the computation so that it comes out nice. But this thing is a Lyapunov function, and it's also convex. So so it's in fact strictly convex. So this thing here is strictly convex, and the other term is linear, so it's convex. So it should have only one critical point. Yeah, convex functions have only one critical point, and it turns out that this critical point is very easy to find. So now there is an easy theorem, so that this F is uniquely minimized among probability measures by a thing called the Gibbs measure. So in the Gibbs measure, so rho beta is e to the minus beta h over z, and z is just a normalization constant, e to the minus beta h dx dp. Okay, so that's the unique minimizer of that thing, and then the corollary. So for nice V and rho naught, rho of dot t converges for time goes to an infinity really to this rho beta. Okay, so there is a unique limit state, and okay, so a reasonably nice version is CEG Gero and near, so it's something like 2004. So they have a reasonable rigorous version, but in fact, so also I think this field is a bit in a bad shape in that for these Fokker-Planck equations, people always assume quite smooth vector fields. But when we really want Lennard-Jones forces, so people have not even proved existence of solutions to the Fokker-Planck. That is very sad, but I checked with many people. It's very sad. Nobody can even prove existence, but it should be rather trivial. But the thing is this awful singularities, but the particles kind of never go there, but one needs some kind of estimate how unlikely it is that they go there. And get the existence and also this proof. So so open. So let's say for rough potentials, e.g. Lennard-Jones. So for Lennard-Jones interactions, that should be absolutely no problem to do all this rigorously, but nobody has done it, which is kind of pathetic. But you know, I apologize. So for the mathematics community, to anybody who's from flight physics. Okay, so so now once we have this, so what happens? So, okay, now let's do the proof because it's one line. So the proof of this second theorem. So that is easy. We just take naught as the functional derivative. So if I do a perturbation f of rho plus epsilon phi. Okay, assuming there exists a minimizer, okay, so, but it's a convex functional, so that follows from standard convex analysis that there exists a minimizer. Just use direct method over characteristic variations, and then take the functional derivative. So this is like, so for the rho, for the first term in the free energy here, so we just get h times phi, and for the second term, we get the derivative, so the beta inverse is in front, stays in front, and then the rho log rho, it's basically, it gives me log rho minus 1 as a derivative, and then that thing times phi. So for all integral phi equals naught. Yeah, so my perturbations should preserve being a probability measure, so they should have integral 0. So we should preserve the mass, and
Phi should get support.
yeah, so it should have support on the, but you know, the minimizer will be everywhere positive, so that kind of comes from this infinite slope here. If it was not everywhere positive, you find a better competitor by moving a bit away the mass. Actually, so the minimizers will be positive. So if the phi is compactly supported and sufficiently small, it's always admissible. Okay.
Just check. So from last sheet, when you say 300 possessive 300 time t, in the theorem that you have to
Okay, so now we're at the stationary theorem. So now we're just we're minimizing it on time independent profiles. So we are done with the time. So now the rho is just independent of time. So it's in the second problem. I just look for the minimizers of that. And so the theorem about the Lyapunov functional tells me that as time goes to infinity, the dynamics should converge to the minimizer of that Lyapunov function. But now we are done with it, but I'm trying to figure out what the minimizer is. And so that's now minimized among probability measures. I mean, this is really on R to the 2dn, so not time dependent. So it's really time independent probabilities. Okay, so does that answer?
I think so. Let me, the thing I just need to think about, like you said, was good.
Okay, so at any fixed time t, you have some probability distribution on the phase space, and the free energy of the system at time t is this functional evaluated on that. And so the free energy is a functional on probability measures on the phase space. So on P of R2dn, so to speak. So Sorry?
What is the Lyapunov function?
Oh, a Lyapunov function. Oh, it's a function that decreases along solutions. Okay, so Lyapunov functional. So f of rho of dot so is less or equal f of rho of s for all t bigger or equal s and for all solutions. Okay. So it's a notion from dynamical systems theory. So okay, so here we go. So yeah, so now now I wanted to derive the Gibbs measure, so I do it as follows. So this tells me that the integrand then h plus beta inverse log rho minus 1 integrated against all constant test functions is 0. So then this has to be equal to a constant. So sorry, integrated against all test functions which integrate to 0. So if I had this integrated against all test functions, I would get h plus beta inverse log rho plus 1, log rho minus 1 is 0. Now I get that it's a constant because I can only integrate against test functions with integral 0, so I don't know what the constant is. In fact, it's good that I don't know what the constant is because I will need it later to normalize this thing. Okay, so let's solve the elementary algebra problem of solving for rho. So then basically log rho is another constant. Let's call it constant. Is a constant prime. So that log rho is a constant prime. Minus h. No. Yes. Okay. So and then times beta. So that's that. And then so we just exponentiate. So and then we get the famous formula. So log is e to the minus h times beta times another constant. Let's call it constant double prime if we solve for the rho, and then this is 1 over the z, since we have integral rho has to be equal to 1. So we get this from normalization. So that's it. So now we have this Gibbs measure, and so now we can do. So finally we can do the low temperature limit. So we did the long time limit, and now we do the low temperature limit. That's very, very easy. So I'm not going to go into theorems, but just draw a picture. So now let temperature go to 0. So beta is 1 over temperature goes to infinity. So what happens to the Gibbs measure? Let's say let's do a picture here. So that's basically here the h, and that's the phase space. So if you look at e to the minus beta h, what should it be what should it look like when beta is large? Well, yeah, can I draw in color on this, Kodina? Can we draw in color on this? No.
Yeah.
Oh. Do you have a nice color?
Red, blue.
Oh, red is
green,
good.
and
Yeah. Oh, very good. Thank you very much. I take the red here. So the typical rho beta, it should sit where the minimas are concentrated. Yeah, the minimum could not be. So this should be the rho beta. Yeah. So is e to the minus beta h divided by this constant. Okay, so it should just concentrate on the minima of the set. Yeah, so that's just this. So basically, so then rho concentrates, so rho beta concentrates on, so it's basically the arcmin of H. And now the arcmin of H, I finally come to energy minimization. So the arcmin of H, so remember the H was basically, so the H was some I 1 over mi pi squared plus the potential energy. And so now this pi squared is basically, so the pi squared is minimized out by putting it equal to 0. Yeah, so the smallest I can make it is make it 0. So the arcmin of H is basically the sets x 0 in R2dn such that x is in arcmin of the V. So what we should see at low temperature is P's, which are essentially 0. So that's what we saw in my simulation. So this little crystal, it kind of still wiggled a little bit because my temperature was not exactly 0, but it just wiggled a little bit. And we had a configuration which was actually minimum. Okay, so X in arcmin V. And so then let's do a summary of this, and then yeah, we are kind of more or less done with what I wanted to say in the first session. Why did we see crystallization in the Langevin equation with Lennard-Jones forces? Okay, so we saw it. So we waited a long time. So that was the t goes to infinity. We took 1 over beta sufficiently small. So I mean, let's say took sufficiently small temperature. So this was beta is 1 over temperature goes to infinity, and so the third we need to understand the crystallization is then really understand energy minimizing point configurations for this Lennard-Jones like things. So apparently the configurations in arcmin V are close to crystallized. Okay, so that's basically that. So and we want, it was a highly computer aided demonstration so my simulation of Langevin at long time and low temperature was a highly computer aided, highly non-rigorous, so to speak, thing that these configurations in the arcmin V will be close to crystallized. So yeah, what do we do time-wise? I mean, certainly that would be a natural topical break before I get into discussing then this arcmin V for the Lennard-Jones surface with a lot of simplification with the P goes with the. How much? Okay, very good. Yeah. So now then maybe let's get started a bit on this on the second. Yeah, maybe let's should we break for a few minutes or you?
Yeah, but I mean the break is in 30 minutes.
Oh, the break is in 30 minutes. Very good.
Now we do a break and
yeah, okay, no, fine. I follow the instructions. That's good. So
let's just make a big flip.
Okay, so let's okay, so let's say we understood a little bit that
But I wanted to ask a question. So,
yeah, please.
Which is a curiosity. It's like that means the limits of these dynamics is going to be in the argument of B. But do we have some reason that it will cover all the argument of B, or how to protect each part of that?
Okay, so so what happens in practice is you see different minimizers with equal probability. So in the example I showed, I had I had 10 particles. So for 10 particles, certainly for the Lennard-Jones energy, so it's invariant under translation and rotation, and each time I run the simulation, I get a differently translated and rotated state. If I waited long enough, I always got this crystallized thing, but I see an equal probability in this case among all the minimizers. If it's a case where in the Heitman-Radin bond counting case, if I have different minima, then usually under Lennard-Jones, under the true thing used in simulation, they will have slightly different energies. And I sometimes see one of them, sometimes the other, but I get a probability distribution somehow on these different configurations. So one would expect ultimately a sort of uniform distribution on all the minimizers. So that's what I would expect. But in the simulation, it will then, okay, so if it might then depend a little bit on the initial conditions, because you might evolve more easily due to entropic barriers or something like that to one than the other. But I would expect a uniform distribution on all the minimizers in the limit. And I'm sure in special cases or for nice potential energy surfaces, this is a rigorous theorem. So yeah.
By the way, I would like to wish you luck proving your theorems for this Heitman-Radin theorem model, which has the range going to 0, time going to infinity, and n going to infinity.
Well,
I wish you
yeah,
with the rigorous proof of how these limits have to be done.
Oh, no. I mean, the how the limits have to be done is very simple. So for the rigorous theory is you do them in the right order that makes the mathematics simple. So that means you first let time t go to infinity, then you let temperature go to 0, and then you take the brittle limit. So this order of limit. So in physical terms, it means the p is much bigger than the than the beta, which is in turn much bigger than the capital T. So that's in terms of the regimes. So that's the regime covered by the theorems. So but that's the difference between physics and math. I think it's nevertheless very interesting to find some regime where one can really nail this crystallization phenomenon. But it's really only this regime where the analysis applies. And in practice, maybe as a physicist, you really want the phase diagram. Yeah, you want to see, for example, below which betas you get the liquid or the gas or the solid and so on. So that's a different. Yeah, maybe a question then.
Regarding the earlier exercise, the energies of the function. So, at least in some cases, the same equation for the energy, but looking at the theorem of very specific time, what is true of the more general conditions that
Okay, so that's a very interesting question. So steepest descent dynamics. So let's start with the heat equation. So that would mean for the simpler stochastic model. So that if you just have x dot equals I mean, it's sort of minus grad v of x plus sigma w dot. So that would be a sort of Ornstein-Uhlenbeck process, which is first order in time, and you have the noise. So x is in RD, so random variable in RD. So if you solve this SDE, so then by the Greg Pavliotis rule, or yeah, whatever, no, the rule from Greg's book, but so then we have dt rho is sigma squared half Laplacian rho. So I mean here it's just rho is p in p of RD intersect L1 of RD, let's say. Okay, so and then this diffusion equation is really so for the so in this case the Lyapunov function, so to speak, so the free energy, so the free energy would then be so in this case f of rho is integral, so you have no kinetic energy here because you have, it's a sort of overdamped limit if you want, so just kinetic energy. So then you have v times rho, so the v instead of the h, and now it's just an RD, plus so integral so rho log rho, so the entropy, and so basically so this equation is a free energy for the heat equation, and so then what happens is that this is the steepest descent for the free energy under the Wasserstein 2 distance. Okay, so that's the famous time stepping scheme by Jordan, Kindler, and Otto. So in this case, there's an even nicer proof of that this is a Lyapunov function, because it's even the functional that's driving the evolution by steepest descent. So now in the kinetic Fokker-Planck case, this is more difficult because the diffusion is only on the momenta, not in the positions. So it's not a, so the if you want, the generator of the dynamics is not the Laplacian, which is the elliptic operator, but the kinetic Fokker-Planck operator, which is only hypoelliptic. So it has diffusion in some components of the phase space, not in others. And then it's not steepest descent anymore. So there is a framework that was figured out by people like Marc Pelletier at Eindhoven, or people like this. So it's called generic. So it's a sort of general formalism for thermodynamic models that include diffusion and transport. And so, but it's a little more complicated structure. It's not a gradient flow. So, it's not a steepest descent of the free energy. So certainly you have to work to show its decay. But you know, you should come to the class on this, because I structured this with a handout and, you know, with a sheet, and you know, we can at least figure out it's a Lyapunov function, but it's not steepest descent. So, but I mean, nature has not just positions but also momenta, and you know, Newton already told us that you have molecular dynamics with positions and momenta, and in fact quantum mechanics tells us the same thing. So there is this molecular dynamics, so at least certainly the Hamiltonian dynamics was it's also, so maybe that's another remark I should make. So that's a limit of quantum dynamics. So the Hamiltonian dynamics is a limit of quantum dynamics, and the limit has to do with the mass ratio between electrons and nuclei, which is in practice 1/2000, but in theory it's then 0 in the limit. So, you know, we do something even worse. So if we started from quantum mechanics, we also let the electron nuclei mass ratio go to 0. So it's kind of yet another limit. But in fact, so for this, maybe I use this to do some advertising here. So molecular dynamics as limit of correct Schrödinger quantum dynamics. So we wrote, I think, luice paper about it about a few years ago, so maybe 2015. So this is together with Luigi Ambrosio, Alessio Figali, myself, Yannis Giannoulis, and Thierry Paul, who's in Paris. And so we wrote a rigorous paper actually as how this molecular dynamics emerges as limit of quantum dynamics. But this is only for the Hamiltonian part. So what is open is sort of Langevin, I should say Hamiltonian, not molecular, and this Langevin or something similar as limit of dissipative quantum dynamics. So that's another thing that, it should be sorted sooner or later. Somebody should sort this out. So when you start from dissipative quantum dynamics, so dynamics of open quantum systems, so that would be something called the Lindblad equation, where you properly account for quantum mechanisms of dissipation, such as in the formalism of quantum dynamics, and then what happens to this in this mass ratio limit between electrons and nuclei. And so there, I would say the situation is a little less well understood. I mean, the other situation is essentially a semi-classical limit, and depending on smoothness or sacrificing rigor, this has been understood a long time ago, that basically quantum dynamics goes to Hamiltonian dynamics. I mean, our claim to fame here is just doing this for rough potentials. Yeah, there's a comment here.
Just if you want to make a big picture, right? I mean, let's not forget special relativity, because if you have your Lennard-Jones potential in a system n going to infinity, every particle will know exactly where all the other particles are moving. So,
Yeah. So that's but I think the let's say the Schrödinger level quantum dynamics is a well accepted model which would apply to real atoms and molecules in usual regimes, unless very high energies and are involved. So
that's much they sometimes insist on the relativistic direction.
Well, I mean, that depends on the system you model. So when there are very high speed particles involved, and so that happens. Okay, so now it's becoming like a physics class, but fair enough. No, but it's fair enough. So let me answer this since you asked. So when you have heavy metals like say lead or something like this, or even already gold is pretty heavy. So then the core electrons, the ones very close to the nucleus, they move very, very fast. So the heavier the atomic nucleus, the faster the particles. So for the hydrogen atom, it has about, so typical electron has about 1/100th of the speed of light. So that's very slow in quantum terms. So it's 1/100th of the speed of light. You don't care about relativistic velocity addition. In gold, it goes to like 1/4 of the speed of light. And so at 1/4 of the speed of light, you have to be a little careful with how you add velocities and stuff. And then in the spectra of gold, you see relativistic shifts. But let's say for helium, helium, argon, whatever, first, second period atoms, you couldn't care less about relativity. But for heavy atoms, the inner electrons get very fast. And so then you use these conditions. But I think, look, I tried to do a good job to get to minimizing classical potential energy services, and now you want me to start even earlier. So then we need another school. I think I want to.
It would be nice.
Well, so here we go. So okay, so yeah, let's get a little bit started on this energy minimization. So what I want to do now is go to the so second is so the second is let's do here So ground states of the 2D Heitmann Radon model. So let me start on this. So so at least write some theorems. So so let's do so we have the so the model is we now minimize E of x1 to xn is sum I less than j v of xi minus xj. And so so x1 xn in r to the 2 cross r2 pairwise distinct. So that's my configurations. So now this is R2, and these are the xi's. So these are the xi's. And so now I want to take this special potential. So V Heitmann Radon of R is we take the lim as p goes to infinity of Vp to p of R. So the Lennard-Jones P to P of R is R to the minus P minus 2 R to the minus 2P. So why did I, sorry, can we see this here? So why, yeah, so why this one? So this is a good normalization for these Lennard-Jones potentials because then the minimum is at 1 and the depth of the minimum is at -1 and this is 0. So this is Vp2p. So that's why you need to take the -2 here. So that's exactly the normalization that fixes the depth of the energy well and the position of the energy well. So particles want to have distance 1 and the reward for binding is -1. Okay. So and then when you let p go to infinity, what do you get? Well, this thing gets narrower and narrower. Oh, I think I use this wonderful red pen again. So when p gets large, so this thing gets basically looks like this. So it's p much bigger than 1. Yeah, so it gets narrower and narrower, so that just scales the width of the well to 1. And so this gives me plus infinity for r less than 1, -1 for r equals 1, and 0 for r bigger or equal than, sorry, not bigger, bigger than 1. So that's this Heitmann Radon potential. Actually, viewing it as a limit of the Lennard-Jones is our work, not Heitmann and Radon's work. Okay, so but it's a natural limit. After you naturally normalize the Lennard-Jones, it's a limiting case. And then, of course, as usual, you expect that when p is sufficiently large, the error is similar. And some of the stuff I say will also apply to the general Lennard-Jones. Okay, and so so then, what is the Heitmann Radon theorem? It says the following. So yeah, so let's look at the Heitmann Radon theorem. Let's see. Maybe introduce the triangular lattice. all minimizers are up to a single rotation and translation. Subsets of the triangular lattice, so L, which is sometimes called A2, so it's IE plus JF, IJ and Z. So it's IJ and Z. And so then let's draw this here in 2 dimensions. So so if that's the origin, that's the E, and that's the F. Okay, so that's this famous triangular lattice. So E is, let's say, 1, 0, and F is a half, and square root 3 halves. Okay, so that's the triangular lattice, and so the result is interesting because it's really sort of all ground state configurations for any n. So for any n, all minimizers of this Heitman radiant energy are up to rotation and translation subsets of the lens. So so yeah, the examples of sets that look a little bit weird I showed on the slides, but that's a very nice exact crystallization result. So in this limit, maybe I want to also say, yeah, that the proof in that paper was criticized by people. So yeah, I'm personally not 100% sure how rigorous or correct it is, but more or less people fixed the gaps during the years. But what we want to do is a new proof of this. So that's what I want to at least get started in explaining. And so this is this work by myself with my co-worker with Lucia De Luca. So she was a postdoc in my group and now is a professor in Rome. So we derive using discrete differential geometry, and so maybe I could get started here on this. So so the idea is we go from particle configurations. So then the next thing we do is a sort of bond graph, which is so that's one thing. And then okay, to do the bond graph is not the innovation, but the innovation is here. So there is a suitable notion of discrete curvature associated with that graph, and that will give very nice way of and so this gives a sort of simplified decomposed energy. So and then we work with this simplified energy. So maybe I can at least explain. So what we do with the so how do you so the viewpoint was that these sets are endowed with not enough structure, and it would be nice to endow them with more structure, and then we see what's going on. And so let me at least define this and see what we do. So I thought it's still readable.
Right now, text is not
Ah, okay. What I'm writing next is not readable. How can you know? Because I haven't written it.
right.
Oh, but I haven't written anything that wasn't readable. How do you know what I would have written? Okay, very good. So configurations. So configurations is a sort of x is x1 to xn in R2, and then so the xi mutually distinct. And then let's do the bond graph. So so we put an edge. So we fix bond range alpha beta, which should contain the point 1, which is the minimum point of the potential, and naught less than alpha less or equal 1 less or equal beta, and we also okay, and so then we can define the edge set. So it's basically this xy, so xy, so x and y are in the configuration, and alpha less or equal x minus y less or equal beta, and so this Euclidean distance on R2. Okay, so I have the Euclidean distance here on R2. And so now, so the key point that is simpler in 2 dimensions is that there's a condition when this is a planar graph. So provided when beta is less than square root 2 times let's see, okay, so when the beta, so the largest distance at which you call something a bond, does not exceed square root 2 times the minimum distance, then bonds cannot cross. So this is a planar graph. So, and that's a very nice thing, because so planar graph means edges do not cross. Okay, and so then so in fact, so this condition that so there is a sort of remark. So for the Heitman-Radin model, you can do this very simply, but because the only sensible choice of bond length is just 1, because you're penalizing plus infinity when the particles are closer than 1. So for Heitman-Radin, so just take alpha. So just take beta equals 1 is less than square root 2 times d min, but this is also 1 in this case. So this is okay, but it's also for the 612 Leonard-Jones, for example, this condition is also okay. So so let's say there exist such alpha beta if d min is bigger than 1 over square root of 2. So that's easy to show. So these two conditions can be solved when the minimum distance is bigger than 1 over root 2. So I mean, then we can shorten this. I mean, then for Heitmann-Radin, we have basically, so it's okay because the minimum distance, so d min is equal to 1. And for 612 Lennard-Jones, it's also okay for minimizers. So that's a result by Xavier Blanc in 2004. So in fact, yeah. Okay, yeah, very good. Yeah, perfect. So then we have this bond graph. So for the Lennard-Jones, in fact, so if you have for the 612 Lennard-Jones, so if x minus y is equal to 1 over square root 2, that would be in this case so the v of x minus y is basically plus 48. So it's much bigger, but let's say v at infinity minus v of 1 is just minus 1. Okay, so this is ridiculously expensive to compress particles to the distance 1 over square root 2 in the standard 612 Lennard-Jones, which are used in the simulations. And in this case, it is a theorem or proposition or whatever by Xavier Blanc, who checked that for ground states, the distances are never that small. So the proof is very simple, just rearrange the particles and gain energy. Just take one of the particles out and move it off to infinity, and that lowers the energy because you have plus 48. Okay, so here we go. So yeah, so then you have this planar graph. So now planar graphs are nice because you can do graph theory. And so let me at least maybe define, okay, so no, I think, let's, okay, so I did the boring thing. I defined the Heitmann-Radin model and I defined the bond graph and I showed it's a planar graph, even for soft potentials like the standard 612 Lennard-Jones used in the simulations. So my particle configurations are planar graphs. So that's what I have. And then this afternoon, I'll start from there and explain the curvature. So yeah, thanks. And let's